Hello, I am Alper Vural from Istanbul. I'm going to present you the n-dimensional lattice path enumeration. In the literature, lattice path is defined as one of the paths from one point to another in a model that consists of horizontal and vertical paths that intersect each other perpendicularly. Various researches have been carried out on the lattice path for many years. These studies gained momentum, especially after the 19th century, and the most comprehensive studies on the subject have been made in recent years. We refer 13 for a history of lattice path enumeration. We enumerate lattice paths in an n-dimensional space for a fixed set of vectors Vn, who consist of all vectors that have coordinates 0 or 1 besides the 0 vector. Our goal is to find a formula that gives number of paths from the origin to the point L1, L2, Ln using the vectors in Vn for n greater or equal to 2. We usually refer to these vectors as step. Figure below gives concrete examples of lattice paths in 2 and 3 dimensional spaces. For example, this path right here is at 3, terminates at 3, 2, and this path right here terminates at 2, 2, 2 in 3-dimensional space. There are 2 to the power of n minus 1 steps in Vn, each aj with one smaller or equal to j, smaller or equal to 2 to the n minus 1 represents a different step in Vn. Rj is the number of aj steps used in a path. A bundle of steps is an unordered group of steps that do not have to be different. Given all values of Rj, we can form exactly one bundle of steps. For example, if n is equal to 2 and R1, R2, R3 is 3, 1, 0, we get the bundle A1, 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 A3. There are 3 A1 steps. Number of all possible paths in n-dimensional space that doesn't have to terminate at a fixed point can be found with the following formula. All possible bundle of steps are generated with the sums, these two first sums. And for a given bundle of steps, these two second, this sum and this product finds all possible permutations of that bundle. We find a function that determines whether a path terminates at the point L1, R2, Ln, the point that we want to go to. Determining the terminal point of a path is the same as determining the terminal point of the bundle that the path was created. It follows because all arrangements of a bundle of steps terminate at the same point. We systematically assign vectors to the notations of the form aj. First, we establish another notation for steps. Let h1, h2, hn be a step in Vn. Note that these h1s are just ones or zeros. We write db to the notation of that step for every hp equals 1. And we have u smaller y for du, dy. For example, the step 1001 is given by the notation d1, d4. This notation tells which axis the steps move on. Note that the notation d1, d4 represents 1001 only if n equals to 4. For example, d1, d4 represents 1010 if n is equal to 5. We call the length of a step is the number of axes that the step moves on. That's equivalent to the number of ones in the vector h1, h2, hn, and also the number of db terms in the notation of that step. We start sorting the steps by their length. The length of the steps ascends from 1 to n. That means that the notations aj with like that represents the steps with length of k plus 1. And for a fixed length, the arrangement is similar to an alphabetical arrangement. Assuming db denotes the bth letter in the alphabet, we do the classical alphabetical arrangement. The arrangement of steps for n equals 4 is shown below. For example, this A5 vector can be think as AB. This A6 is AC, AD, BC, BD, CD. We determine the distance traveled on a specific axis for a given bundle of steps. We call this axis the observed axis and represent it with di. We find all steps that have di in its notation. We can show such steps with in this form, where p is the number of axis that's written before the observed axis, and k plus 1 is the length of the step. The valid interval for I is 1 to n, because I is the observed axis and there are n axes in the n-dimensional space. The valid interval for k is between 0 and n minus 1, because we said that k plus 1 is the length of the step, and the length of the step can be 1 to n. The valid interval for P is maximum 0, k plus I minus 10 and minimum k, I minus 1. We find all steps that travel on ith axis for fixed values of I, k, and p. We denote the function that finds the coefficients of all such steps in n-dimensional space by fn I, k, p. We say that all steps with given I, k, and p values whose parts before the observed axis are the same form a section. For example, when observing D6, D3 in 6-dimensional space, D1, D3, D4, D1, D3, D5, and D1, D3, D6 form a section because the part before D3 is fixed. Let the part before the observed axis be fixed, more specifically D. Let AQ plus 1 be the step D, DI, D plus 1, DI plus 2 consecutive terms here. Then all AJ steps with Q plus 1 smaller or equal to J, smaller or equal to Q plus M minus I choose K minus P move on the ith axis. Thus they form a section. For fixed values of I, K, and P, there can be I minus 1 P different parts for the observed axis because there are I minus 1 different dB terms and we have to choose only P of them. For example, if I is equal to 3 and P is equal to 1, there are two different parts. That could be D1 and D2 and we get sections D1, D3, D2, D3. If the part before the observed axis is D1, D2, D dot dot dot, DI minus 1, pretty much all of the consecutive terms, then the first step in this section is exactly this. That's the first step with the length of k plus 1. If the part before the observed axis is missing some of these dB terms, to find the first step in the section, it's required to add more terms besides this term. We create sequences that have B for each dB term missing in the part before the observed axis. The empty sequences are subsets of 1, 2, I minus 1 with I minus P minus 1 elements. All different subsets of that set with I minus P minus 1 elements are the sets in the form like that. We found empty sequences for I is equal to 4 and I is equal to 5. These are the empty sequences. For each missing term in the part before the observed axis, it's required to add m minus mt choose k minus gt. We found the following gt sequences. The sequences on the top are empty sequences, and the sequences on the bottom are the gt sequences corresponding to that empty sequence. And we found the following relation in gt sequence. Finally, we can write fn ikp as follows. If I is equal to p plus 1, then there are no parts missing for the observed axis. Thus, there are no empty or gt sequences. So we wrote fn ikp p is wisely like this. Finally, the distance traveled on ith axis is k equals 1 to m minus 1. P's interval is like that at fn ikp. Define Rx 1 if x is equal to 0, 0 if x is not equal to 0. Then the total number of paths to the point L1, L2, Ln can be found with the following formula, where we subtract the distance traveled on the ith axis from the distance that we want to travel. And if all of these terms are 0, then we can get a 1 here. In n-dimensional space, the number of paths to the point 1, 1, 1, 1, 1 corresponds to the number of weak coordinates of a set consisting of n elements. These are the total number of arrangements n competitors can have. The answer is not just n factorial, as competitors can have equal points. Let K be a set of vectors and L, L1, L2, Ln be the number of lattice paths from origin to the L1, L2, Ln point. Then the recursive relation in this sequence is as follows. Let M P to P prime denote the number of lattice paths from P to P prime without restrictions. The number of paths from P to P prime that do not stop at the lattice points in a given set R can be computed by the following algorithm. Let Rn be an M element subset of R. For pi element Rm, calculate the quantity -1 to the power of m and these for all permutations of Rm. There cannot be more than one non-zero value, and if there is one non-zero value, note it down. Do this for all subsets of R. The sum of results in the number of paths from P to P prime that do not touch points in R is that the sum of those numbers. We multiply by -1 to the power of m because of the inclusion-exclusion principle. These are my references. Thank you for listening.